All right, so when dealing with a two-dimensional plane is definitely a lot easier to analyze this using the plate. So it first tells us our vector is 0, comma 1. That's what a 0, 1 means. So 0, comma 1 puts me right here at this 90 degrees on the y-axis. And then it says if I was to rotate 45 degrees clockwise from this point, where's that take me? That way, which is 135 degrees. So that would be the coordinate. Then it says reflected across the y-axis. So to reflect this across the y-axis, where's that put me? 45 degrees. So this would be the coordinate or the vector in which this has moved. All right. So that's your answer. Write it as a resulting vector. Ow. Oh. So 0, 1. Man, I twisted my knee, I think. Um, so we started at 0, 1 because that's what it told us. 45 degrees counterclockwise was as at 135 degrees. And then it says, then reflect that across the y-axis was as at 45 degrees. So then that coordinate would be my vector. So that would be square root of 2 over 2, square root 2 over 2. Questions? Go ahead. I didn't divide. Uh, then the next question basically says, all right, take this exact same V, but this time reflect it across the y-axis. Well, if I'm on the y-axis and I reflect it across the y-axis, do I move? No. You actually stay right there. Then it says from there, now move 45 degrees counterclockwise. Where's that put me? It'll be 135. So originally I was at 90. I reflected across the y-axis. I didn't move. Then I moved 45 degrees counterclockwise, which was me at 135. So in this situation, this is now my answer. What's the question? Sorry, I heard from David first. Okay, so on same process, commute or compute? Driving? Uh, that's what I would most say. That I would say the word compute instead of commute. But yes, it means do these equal. So in this situation right here, so again, we start at V, so that's 0, 1, that's at 9 degrees. This time I reflect it y-axis first. So if I'm on the y-axis, that would be reflected across the x-axis. So if I'm on the y-axis and I'm reflecting the y-axis, I cannot move, right? Because right, if I fold it like this, I'm still in the same spot. Then from there, I then move 45 degrees counterclockwise, which puts me then at 135. Correct. So that would be the coordinate goes. Yes, sir. Correct. It goes from here to here. If I'm going from here to here, I'm now reflecting over the x-axis. Think of reflections as if you folded that circle at that reflection line, that would be where your point would land. So if I'm reflecting over the y-axis, I would have to take my plate and fold it like this, and notice my point is still in the same spot. Versus if I reflect it across the x-axis, now I've landed on 270. So wherever the reflection line is, that would be where you go. So that what you also missed is we reflected across the y equals x. So like if I had to flip it like this, it would probably land probably like at 300 or something, or 315 or something like that. I think that one we had to do the math because it would be weird numbers, but that would be what the concept is. Wherever the reflection line is like folding that plane in half and seeing where does it land. That makes sense? Any other questions? Yes. We're actually going to be doing that in the next step. Yes, because that's what we're going to be doing mathematically on this one. This one here, we were just physically moving it, but we'll do the algebra part here in a second. So you actually probably just use those exact numbers for the next part of the question. All right, this last part of this open exercise, did these linear transformations commute? That's a weird word. I would say compute, but I'm not an English major. So basically what that means is, do both of these vectors equal the same thing? No. So that means that no, the two vectors did not equal, or whatever else you want to say there. However you want to say that. Listen. Questions? All right. So again, beforehand, up to this point, every transformation we've done has always gave us the same answer, regardless of how we've gone. But now we end up with situations where sometimes it does not, which then if you can find one counter argument, that means we cannot flat say that multiplication is commutative, which we kind of already knew in multiplication that it wasn't commutative. But we kept on seeing some that kept on working. So on exercise 1, it says let A equal the matrix that corresponds to a 45-degree rotation. So what it's basically stating is going back to our 2x2 matrix of transformations with dilations and rotations. Let's form a matrix with that. So when I have something like this, again, using this form, we're going to form a matrix A. That's what it called it. So we'll say A equals. And then now in this case, it says a rotation of 45 degrees counterclockwise, and then B will equal something else. So do I have any dilation for my matrix A? No. So I don't have an R. So I can kind of just play it like this. So cosine of 45 degrees, because that's where I got in the directions there. And then negative sine of 45 degrees, sine of 45 degrees, and then cosine of 45 degrees. Before I move on any further, does everyone understand how I got this matrix for my rotation of 45 degrees? I just pulled from our, basically, I guess you'd call it the formula or the parent matrix or however you want to look at it, but it just came from the transformation matrix. All right, now from this is not the form that we typically use. So we have to find our coordinates and plug those answers in. So I know at 45 degrees, the answer is the square root 2/2 for both sine and cosine. So I'm going to rewrite that. This now becomes the square root 2/2, negative square root 2/2, square root 2/2, and square root 2/2. Again, the reason this is negative because the formula had a negative. Are we good on how we just made matrix A? All right. Matrix B, I always have to think about it. It's not one I have memorized, but if you do, that's great. We want to try to make a matrix B that corresponds to a reflection across the y-axis. For me, I have to almost graph it. So I have to go, all right, if I have a random point over here, we'll call it a positive and a positive, and I want to reflect across the y-axis, what do I want on this side? Negative, positive. So when I'm trying to form a matrix and I want to multiply by two positive answers, we'll just call them X and Y, and I want the answer to now be a negative X and a positive Y. Again, I'm just making this up because I don't memorize it. You can memorize it and look back in your notes and have it and start and use it. But in math, there's always logic behind it. So if this is my original point and I now want a point that looks like this, what does the first row have to be so that I end up getting a -1? A negative something. What would that negative be if I just want that negative X? All right, -1. What would this one be? 0, because I just want negative X as my answer. So -1 times X is negative X. 0 times Y is 0. So I get just negative X. What would row 2 have to be in order to just get a Y? There it is. If you have that memorized, great. I don't. So this is the logical way to go through the process to see what will cause a reflection across the y-axis. And you could technically have put this point anywhere you want it, because you're still trying to get the same outcome of whatever that new coordinate signs would be. Questions? All right. So now that we have both matrix A and B, it wants us to verify that matrix multiplication does not compute. Meaning, if I do A times B, will it equal B times A? So let's start off with that. So my A matrix is the square root of 2 over 2, negative square root of 2 over 2, square root 2 over 2, square root 2 over 2. And we're going to multiply that by the B matrix. So that's negative 1, 0, 0, 1. Let's see what we get. If I do row times column, what's my answer? Okay. Row times column. Row times column. Row times column. Good. This time positive. Perfect. All right. So there's my matrix. Again, what we're going to test is, well, if I would have done B times A, would I've gotten the same answer? So let's mathematically do it to determine that. So my B matrix this time is now negative 1, 0, 0, 1. And matrix A was square root 2 over 2, negative square root 2 over 2, square root 2 over 2, square root 2 over 2. Row, column. What do I get? All right, so far, seems to be the same answer. Row, column. Positive, because now two negatives make a positive. Now we got a different answer already. Row, column. Row, column. Stays positive. Perfect. So are these two matrices equal? No. So we just proved AB does not equal BA. Questions? All right. So I told you today was a lot of algebra. Yesterday, last 2 days have been a lot of like geometric looking. All right, so that's for two-dimensional. Does this still apply with a 3-dimension? Everyone ready for me to move? I still see pencils moving. So now that you've had it written down, any questions of follow-up? All right. So number 2, it now tells us what our A and B is. And it says now verify that multiplication does not commute by finding the products of A and B. So meaning I guess they don't equal. I feel like some books find a word and they really end up liking the word. Like commute. Who uses that word? Or randomly. Have you ever used taught as a word? Not taught as in teach, but taught as in like tight. Huh, never until I read a book. I've always just used, hey, it's pretty tight. Not, man, that's pretty taut. It means the same thing. It means tight. So oh, that's like a sarcasm. I got you, I got you, I got you. All right. So that's where, I tell you what, y'all try this one. Multiply AB, then BA, and see if they end up equaling before we get into it. So you'll have time to write down. A bunch of zeros and ones shouldn't be too hard of math. You disagree? We can put some numbers in there. We'd be here all day. I'm jealous. I'm jealous. My back hurts and it won't pop. Very nice. All right, ready? Pretty cool that both these matrices actually did equal each other, right? Just kidding. They do not. So let's make sure. Row times columns. What do we get? 0. Row times column. Row times column. Positive 1, because two negatives make a positive. Row times column. 1. Row times column. 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 Perfect. Any questions? I agree with all those answers. Bless you. You're welcome. All right. Row times column. 0. Row times column. 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 0 times 0. 1 times 1. 0 times 0. So we do get 1. It's okay. Well, I don't expect anyone to be an expert. That's why we practice and we learn. Row times column. Row times column. All right, are these two equal? No. Right? So AB, in fact, does not equal BA. Questions on how to show something's commutative or not commutative? All right, cool deal. Let's move on to 3. I will say when I was studying for this one, I struggle with that abstract mind, but I kind of struggled with trying to figure out where this coordinate was without any math. So if you could think of a three-dimensional vector, 0, 0, 1, that basically means it's 1 on the z-axis currently. All right. So if B is to rotate 45 degrees counterclockwise about the z-axis, where would that put me? I think because you're at z at the one space, and then you rotate around the z-axis. Mm-hmm. But it says the z-axis. So you're saying, all right, if we're at 1 on the z-axis and you rotate 45 degrees around the z-axis, are you moving any? Yeah, but if we're oh, let's see. We moved it off the z-axis. Just like okay, and then you're saying what's the coordinate there? Where's the 0, 1 coming from? Well, it's about the z-axis, meaning not about, but like around the z-axis. But then okay, so you're saying the answer is 0, 1, 1. Okay, now if you reflect depending on where you fall. Okay, and then you reflect that across the XY plane. Where does that take you? I'm gonna have to plug this in, or not plug in, but I need a graph. All right, so let's look at a 3D coordinate plane. All right, here is my vector right there, 0, 0, 1. That's where that would be, and then we're rotating about the z-axis by 45 degrees, counterclockwise. So that put us. It means around. See, my thing is I don't think it's moving. Like, yeah, it's spinning, but the coordinate itself isn't moving because it's on the z-axis. It would be different if it said like x or y-axis, then it would cause me to move in that direction. So I think that's where I'm at with it. I think because regardless of what the rotation was, because it's about the z-axis and I'm on the z-axis, I don't think I'm physically moving, a lot like the reflection. So then that next part then says reflect across the xy plane. So here's the xy plane. The reflection should then be, but on the z-axis. That's how they did it. All right, so geometrically looking at it, this vector here was just 0, 0, -1, right? So again, what we saw is, um, again, to show it one more time, I know y'all are having a good little conversation over there. Yeah, I see that. So we talked about 3D. So we have a vector, a three-dimensional vector at 0, 0, 1. That means there's a point, well, right there where my little pointer is. But then it says it rotates about the z-axis 45 degrees. Well, if I'm on the z-axis and I'm rotating about the z-axis, I'm doing this. I'm like in one single spot. It doesn't matter what I'm rotating, I'm still going to land in the exact same spot. Versus if it said X or Y, then I can rotate around the X or Y. So since I rotated around the Z axis and I physically didn't move, the next part then says reflected over the XY plane. Well, if this is my Z axis and this is the XY plane, if I reflect over there, I should then be at a negative value on the Z axis. So that's how we got 0, 0, -1. I'm glad it made sense to you because I did this like 3 times on my own. I was like, then I did the math. I was like, oh, okay, that makes logical sense. Yeah, but the issue, not like this. Like there, you can do the math to figure out what the answer is going to be, which is what we're going to do next. Like right now, we're just looking at abstractly. But the next question is going to be the same question, but algebraically. So you can use the algebra to figure out what your answer is, given, hey, I want you to do this, this, and this. Yeah. A 3 by 3 matrix instead of a 2 by 2. That's it. And that's what we did in the last 3 lessons. Okay, so let's look at B this time. B says, what if I was at that 0, 0, 1, and then I reflected the XY plane first, where would I be? 0, 0, -1, and then rotated around the x-axis, where would I be? I would still be in the same spot because regardless of where I'm on the XZ axis, I still haven't moved. So I can see that I get the same answer. So when we look at this, let's verify algebraically that the two products of the corresponding matrices is the same regardless of the order of which they are multiplied. So here we go. So producing our 3 by 3 matrix. Again, it's a lot like that one, but remember we put the cosine and sine in the spots at which the axis doesn't get moved. So we'll call this first one, we'll call A the rotation around the z-axis. So if I'm rotating around the z-axis, what axis is not being moved, Hannah? That's right, Hannah. It is the silent axis. We also call it the z-axis. Hannah, wake up with me. But you didn't respond. All right, so yeah, because the z-axis makes those z's as we're taking a nap and stuff like that. So that's perfect answer. So that means that what row doesn't move or doesn't change? The z row. Now, which row affects the z-axis? Which row? Which is the third row? So in a 3 by 3 matrix, since the z-axis is what's being rotated about and not moving, that third row will remain 0, 0, 1 because it's not moving. Now, if I know the third row is 0, 0, 1, what do I know about the third column? It's 0, 0, 1. Now, to figure out these two missing, this is when I then plug in our 2 by 2 transformation matrix into the 3 by 3. So since we're rotating 45 degrees, this will then become This part I would expect y'all to be able to do. So cosine of 45, negative sine. You can put the answers. Cosine of 45. Nope, I lied. That's a sine. And then this is cosine of 45. Again, cosine, negative sine, cosine, or sine, cosine. Pull it from the coordinate. I'm good with that, Luke. You can just plug in straight in the coordinates. So we know this is the square root 2 over 2, negative square root 2 over 2, 0, square root 2 over 2, square root 2 over 2, 0, 0, 0, 1. So that's my matrix A. So this is defining that I have a 45-degree rotation around the z-axis. All right, so this is based off the last 3 lessons. This is the part that I expect you to be able to do. This, thinking about it, great if you can, but not an actual test question. You can always use the algebra to get there. You good there? Okay. Sure, as in like we get it, or sure as in I don't really get it. So that's I get that response a lot. Like I'll ask like something and I get the answer back. Sure. Okay, so you don't want it. Okay, cool. Sure to me means like I don't care. Give me that yes. I get it. Absolutely, right? This right here has nothing to do with this. This is the matrix transformation. So if I was to take this matrix transformation, multiply it to my next B, get a new matrix transformation, and then multiply it to that first vector 0, 0, 1, I would then get this as an answer, which we'll do here in a little bit. Right now, we're just forming our matrix A for a 45-degree rotation around the z-axis. Matrix B is was there a reflection? A reflection over the xy plane. Okay. So if I'm reflecting across the XY plane, what axes are not being affected? X and Y. So this will remain 1, 0, 0, 0, 0, 1, 0. All right. If I'm reflecting across the XY plane, the XY is still the same. What's being affected? And if I'm flipping over from a positive to a negative, or even a negative to a positive, what should that Z row be, that third row? 0, 0, negative 1 to cause the sign to change. So this right here would show me a matrix that is reflected across the XY plane. So again, XY did not change, just the Z value. We good with these two matrices? All right, so our goal is to see, does A times B equal B times A? Because we just saw it earlier with a two-dimensional shape that it did not. There we go. The B matrix, what B is going to be the reflection across the XY plane. So if I'm reflecting across the XY plane, the XY plane is not moving. So that means the x-axis and y-axis results will be the same. The only thing that's reflecting across the xy plane is the z-axis. We keep it's like the identity matrix. That's where we start. Yeah, okay. So you start here. This is where everything starts from. That's why I was like, all right, the z-axis is not moving. That means the third row and third column are not changing. But then the x and y-axis are, so there's the corresponding coordinates for it. Here, xy plane reflecting, so that means x and y remains the same, but now the z is changing sign. To cause that, I just need to multiply by -1. Good questions there. All right, so what I want y'all to do is figure out what A times B is and what B times A is and see what the answer is. So I'll give you some time to do that, and then we'll check it. On part C, yes, we're still on part C. Get both. A times B and B times A. Yeah. It's like you're doing the rest of it. You're figuring out, all right, what is and see if it's true or not. Hmm? Yes, ma'am. Yeah, we didn't need one today. A times B. What do you mean by everything? Are you saying like you'll have all the square roots of twos and stuff? Oh, I see. Okay. I agree. All right, due to time, I'm gonna go ahead and kind of go over them. So you saw that both of them are different, right? All right, that's false. They should have been the same. All right, so row times column would just give you the square root 2 over 2. Row times column would now give you negative square root 2 over 2. Row times column just gives you 0. Row times column gives you the square root 2 over 2. Row times column gives you the square root 2 over 2. Row times column now gives you 0. Row times column, row times column, row times column. So I do agree. It's basically everything's being multiplied. It's the same, but the z turned into a negative one. And when you do this, you can see that you'll end up getting the exact same answer. This one here. So I took row. So really, when you have matrices like this, it's really just the x-axis that's being affected. So there's your answer there. When I then take this row times this column, it's only the y-axis that's being affected. So it'll be the middle one. This row times this one will just be the z-axis. So in that case, it's 1 times negative 1, which gives me negative 1. And then you kind of go through that same process. It's nice when you're multiplying by ones. It's different when there's a whole bunch of numbers going on because then there's multiplication and adding, and that can be time consuming. Questions? So this worked. Is there a pattern of things that will always work? Let's determine. This is the last part of the lecture. Part 4, or number 4, we're going to make our own question. We're going to write two matrices in this form of AA negative BB, and we're going to verify algebraically that the products of these two matrices are equal. So we're going to let A, because we're going to come up with two of them. Huh? Well, in the room that you have left over in 3, yeah. All right, so give me a number for A. Okay, I heard 7. I heard 1 for B. All right, there's our first matrix. I need a new A. I heard 18 and 2, but goodness. There you go. So there's your two different matrices. What we're going to do is we're going to prove that A times B equals B times A every time that this is the pattern. All right, so here we go. So A times B Might need one on this one. All right, row times column. Seven times 18, that's 78, 56, 56, 126. Okay, 126 minus 2, 154. Whoa, yeah, 124. Sorry, 124. 7 times negative 2 is negative 14 minus 18. What is that? Negative 32? Negative 32? You have the calculator. What's negative 14 minus 18? Okay. 18 plus 14. Negative 2, we just determined was 126. So negative 2 plus 126. 124. All right. Let's do B times A. Does it give me the same answer? Eighteen times 7, we determined was 126. Negative 2 times 1 is negative 2. So what's 126 minus 2? 124. 18 times negative 1 gives us negative 18. Negative 2 times 7 is negative 14. Negative 18 minus 14 is negative 32. 2 times 7 is 14. 18 times 1 is 18. 14 plus 18 gives me 32. 2 times negative 1 is negative 2. 18 times 7 is 126. Negative 2 plus 126 gives me. These do, in fact, equal. All right. So when it's in this form, we tend for this to actually be a true statement. Right? And if you recall, this is basically a rotation with a proper scalar on both of them. All right. So let's look at part B. It's only 2 more parts, guys, in 5 minutes. Right? Each of your matrices has a complex number. So what did we just get? If I was to take this back here, if I want to write this as a complex number, remember from our previous lessons, if we wanted to know what the specific rotation was, we just paid attention to the first row. The first row always told us where the rotation was. It might have a scalar, which we would then have to solve a little bit, but it always told us what the answer was. So in this case, what's our answer? As a vector or a complex number. All right. Doesn't need to go in B. The only thing that needs to go in B would be 124 plus 32i. That first row, when it's in the proper transformation matrix, that first row is always our answer. All right. So in this case, my complex number here would be 124 plus 32i. That would be if I took a vector 1, 1 or something like that, and I did both of these transformations, this is where it would land, either direction. Okay. Part C then says, why is the case that any 2 matrices in the form of this have products that are equal regardless of order in which they are multiplied? Anyone have an idea of why this form always works? Let's think about it. Right. But why is that form always going to give us the same answer? Okay, what about that negative? It's just there. This matrix transformation does 2 transformations specifically. What are they? Perfect. So if I rotate around a certain spot and I just dilate that certain spot, is it being shifted any? No, so remember a dilation is like multiplying by a scalar. I can always pull that r out. So I could always write this in the form of this. I'm almost done. All right. So I can always rewrite this like this, where I'm pulling that dilation out as a scalar, and then this will just dictate my rotation. Doesn't tell me where it's being shifted, just tells me where it's turning. So as long as it's written like this, we can always get a commutative product in which it doesn't matter which transformation we do first. What changes is when we do reflections and things are being pulled to parallelograms and it doesn't have this order. So any matrix of two, yeah, both of them were the same, right? Because we got the same result. Is that 124 plus 32i? I don't forget. So any matrix written as r cosine theta negative r sine theta, r sine theta, r cosine theta will be commutative. If it can't be written in that form, then it's not going to be commutative. And that's it. That's all I got.